All right, welcome everybody. This is going to be a pre-recorded lesson for day 4 of our Unit 8, our last unit of the school year, which goes over the galaxies and also some space mission, space discovery material as well. As you can see with our Go Blue, we have the number 1, what is the shape of a galaxy and what can often be found in the middle of them? Number 2, what do we call the cloud of space dust and gas that is often the precursor to creating stars? And number 3, the inner planets have blank melting points while the outer planets have blank melting points. So the differences between those planets, right? Updates also include the Unit 8 vocab, which is not due till next Friday. Other than that, other assignments like another article assignment, as well as online tests and quizzes. Online test and notebook checks will be posted at a later time. But moving on to number 1, guys, this is on page 6, which we wrote down. Moving on there, we've got number 1. We have the shape of the galaxy are going to be in a spiral shape, as you can see there. And again, in the middle of them, kind of helping to anchor and stabilize that shape, is the massive black hole, which spins like a drain. And that's going to cause all the solar systems that are going around the black hole to go around like the galaxy does, right? So pretty cool stuff there. Very similar to the sun and how planets orbit the sun. Secondly, guys, we call the cloud of space dust and gas, we call this cloud the nebula. We call this a nebula, okay? So that is a cloud of space dust and gas that is kind of like the debris, the remains of really kind of like the remains of a supernova, right? So you're going to see that there. And those help kind of form other new stars, baby stars in the future when those gases ignite again. It also kind of creates a bunch of cool elements like the metals we know, like gold, silver, all those things as well. Secondly, guys, lastly, for number 3, the inner planets have higher melting points because they need to be strong to withstand the heat of the sun. And the outer planets have lower melting points because they're farther out, they're colder, they're icy, hence why maybe they're able to survive farther out as opposed to the rocky planets, right? Moving on to our next section, guys, the table of contents. We're going to go over pages 6 and 7, which are the cosmic background radiation. Again, cosmic background radiation. For that one, we're going to talk about all the radiation that's in space. All right. Here's our first practice question of the day. Which of these correctly describes redshift, right? When objects appear red or orange. Okay. Is it A, objects move away, decreasing wavelength? B, objects move toward, decreasing wavelength? C, objects move away, increasing wavelength? Or D, objects move toward, increasing wavelength? What would be the right answer regarding redshift? Okay. And then again, we got to think about wavelength. So if things are getting farther away or getting closer, are the waves getting longer or shorter? Okay. Answer is going to be letter C, guys. As objects move away in space, their waves are going to get longer. Keep that in mind. Okay. Moving on to cosmic background radiation, guys. What evidence is there for the Big Bang Theory? We talk about evidence for evolution. One of those is fossils, right? Well, I want you to begin to think about cosmic background radiation as the evidence for the Big Bang. The Big Bang, right? How the universe started out as a ball of light that expanded, okay? So I want you to go ahead. We're going to write this question down on page 6. What do satellites pick up when aimed at the sky and why? Again, what do satellites pick up when aimed at the sky and why? Let me go ahead and load this video for us and we'll check it out. Again, write this question on page 6. Give this a moment here, everybody, while I get this loaded for us.
The entire universe used to be this color. How's that possible? Let's find out. Outer space looks black, but the entire used to be this color. How's that possible? Let's find out. Stars and galaxies notwithstanding, space is pitch black. So pick a dark spot in the sky and point an analog satellite dish at it. You might expect to get nothing, but you don't. You get static. Pick another point and more static. Move your dish yet again, static. Even accounting for all possible types of interference, no matter how you orient your dish, there's this constant underlying microwave band static that's just always there in the darkness of space, emitting the same pattern over and over. Now, since we pick up this mysterious static from every direction we look, it would seem to be coming from a source that exists literally everywhere on the sky. Problem is, we don't know of any source anywhere that would emit this observed pattern of microwave emission, so where's it coming from? Aliens. No, it's not aliens. It's never aliens. But what if I told you that the source of the static, which we call the cosmic microwave background, or CMB, was the process that formed the first atoms in the universe almost 13.5 billion years ago? And what if I also told you that the source of the CMB also caused all of space to look orange for millions of years? That's right, the universe used to be orange. To understand how this could be true, we first need to take a brief detour into your toaster. Turn on your toaster. The heating elements glow a pale reddish color. That glow isn't ambient light reflecting off the toaster, it's light being emitted by the toaster itself. If you were to analyze that glow with instruments less limited than human eyes, you'd realize that the toaster isn't just emitting pale red light, it's emitting electromagnetic waves of all wavelengths. Moreover, the intensity at different wavelengths is in very specific proportions that trace out a graph very close to this. That emission pattern, represented by the graph, is called the toaster's thermal spectrum, or really an idealization of a thermal spectrum called a black body spectrum. Now, everything has a temperature, so everything has a thermal spectrum and emits all electromagnetic wavelengths. You, a taco, the sun, everything. In fact, it's called a thermal spectrum because the light is generated by the random motions of particles in the material, and those random motions are themselves a reflection of temperature. Now, if you go really low in temperature, down to 2.7 degrees above absolute zero, the peak shifts way into microwave wavelengths and, lo and behold, exactly matches the CMB, and I mean exactly. The CMB is one of the closest things to a mathematically perfect thermal spectrum that has ever been observed. Problem is, space is pretty much empty. There's nothing really in there to have a temperature, much less the very specific.
Just wanted to show you a little bit of that. So when they aim their satellites out into space, they're going to discover background radiation, what's called cosmic background radiation, as you see here. So what exactly, again, we call it here? And by the way, guys, you're going to write this on page 7. This is on page 7, guys, page 7. So what do we see here? What's going on? Okay. If you go out into space, right, there's a bunch of radiation. And if you were to get a spacesuit, you kept your helmet on, you think you're fine, right? Well, your skin can't get exposed to space because there's a bunch of radiation. Just like if you were to put your arm in a microwave. Be really bad. It would burn your arm, right? Burn your skin. Okay. So go ahead, make sure to write this. This is on page 7, guys. This is going to be, let's see here. Yeah. Electromagnetic waves. And where did this come from? This came from the original Big Bang, right? The expansion of the light bulb in space, right? That's where we think that came from. Okay. And these are roaming ions, okay, high energy particles. So space isn't this totally safe floating place just without oxygen. It's got a bunch of radiation waves floating around from the sun and from the Big Bang. Okay, so make sure to write all that. What exactly is cosmic radiation? This is on page 7, guys. Page 7. So early universe, what was it like? It was extremely hot. Early universe was very hot because it was like still recovering from the Big Bang, kind of that expansion. It was super hot, but then it cooled down over time as it spread out. Okay, cool down is very hot. The universe today is filled with electric. So basically, all that radiation from the Big Bang is still floating around space. It's still all over the place, right? It's just spread out, and it's in the form of what we call microwaves. Okay, so this is great evidence for the Big Bang actually happening. The only and best evidence that we have, essentially, that there was a Big Bang, right? Okay, and then moving on here, again, there's kind of a view of that expansion of light that we see there. Let me see if I got another clip here that could be any good. Let's see. Hold on. All right. Looks like it's not loading, unfortunately. Let me see if I get it on the screen here. Hold on. One moment. Having some difficulties. 1 second, everybody. Just trying to get the link loaded.
The beginning of everything. The Big
Then we can kind of see, you know, the Big Bang a little bit again.
Bang is not infinite. In the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity,
Sounds like
and
radiation,
Edwin
right?
Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered,
There we go.
a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to
So again, we kind of saw a little animation that flowed us in on that as well, right? That background radiation was evidence, obviously, right? So let's go before we finish up for the day. Here's another quick question. The early universe was cooler than the current universe. True or false? True or false? That is B, false, right? B, right? Because it's the longer time you wait since the explosion, since the expansion, the cooler it's going to get, right? So the earlier times were warmer, were hotter. Okay, last notes of the day, guys. Let's get into the details on that discovery, right? So when and where, again, discovery of CBR, this is on page 7. In 1965, scientists discovered persistent background noise. It's the same reason why when you tune a radio, in between the stations, it makes those weird noises, right? Those static noises. That static is the background radiation that's blocking the signals in space, right? Or from antennas here on the surface. So the background noise was being caused by the radiation from the cosmos. And again, that came from all directions at a temperature of negative 270 degrees Celsius, a temperature similar to the Big Bang. So hot, cool, again, very many temperatures that match the Big Bang temperatures. Okay. That concludes, I believe, and there's a picture of the antenna that was catching those signals. That concludes our lesson for today, students. Again, don't forget to get caught up with the vocab that's due next Friday. This is Mr. Campbell. We'll continue this lesson another day. This is Mr. Campbell signing out.